Hey guys, now we're going to look at how to solve a projectile motion problem which has motion in 2 dimensions. So imagine you're on the set of, say, a movie, and you have this car that for an action sequence travels over a 16-meter high cliff at 20 meters per second. So we want to know how long it takes for the car to hit the ground and how far from the base of the cliff the car is going to land. So what we can do is draw a diagram of what this looks like. So we have our cliff, we have our car, and I'm going to draw the path of the car as this dashed line. And now what we can do is start listing out all the information that we're going to know from this. So we know the initial velocity of the car is 20 meters per second. But here we have to be careful, because this is the initial velocity of the car in the x direction. Remember that the x and the y direction operate as 2 independent entities in a projectile motion problem. So we worry about one and we worry about the other, and very rarely do we have to worry about both at the same time. One influences the other, but we can work on them separately. So we need to know, does this initial velocity, is that in the x direction or in the y direction? So in this case it's in the x direction, so I will indicate that by putting a subscript x next to that. And if I were to zoom in on this, you can see that I just said the initial velocity in the x direction is 20 meters per second. So we'll zoom out here and get back to an appropriate scale. So now we can figure out what else we've got going on. We're told that the cliff is 16 meters and this thing is going to fall down the cliff. So that's going to be a displacement, but in the y direction, of 16 meters. And something I neglected to do in the x direction, so let's go back and let's fix it now, is I need to declare which direction's positive and which direction's negative. I'm going to call this direction positive, that direction negative, and in the y direction, up will be positive, down will be negative. So this will actually be a displacement of negative 16 meters. And now to add in other things that I know what the acceleration will be, and this is acceleration in the y direction will be negative 9.8 meters per second squared. Just like that. There's the negative sign that I crammed in there. So negative 9.8 meters per second squared. Always, unless there is a force, the acceleration in the x direction will be 0, so we don't even have to worry about it necessarily. And stop and consider this. Do I know the initial speed in the y direction? How quickly is this car moving up or down? And it isn't. So the initial speed in the y direction is 0 meters per second. Now with that, we're ready to go ahead and tackle this problem. So let's look at part A. Slide everything up a bit. So for part A, how long does it take the car to hit the ground? Well, we list out our givens, but now we've got to do this in kind of a different way, because we have givens in the x direction and givens in the y direction. So let's list them separate. In the x direction, we have that the initial velocity is 20 meters per second. And that's it. We could say, if we really wanted to, that the acceleration is 0, because once this leaves the ground, there's not going to be any force pushing it forward or backwards. So our acceleration is 0 meters per second squared. In the y direction, though, we've got all kinds of goodies. We know the initial speed is 0 meters per second. We know the acceleration is negative 9.8 meters per second squared. And we know that the displacement will be negative 16 meters. And when it boils down to it, what we want to find in part A, how long does it take for the car to hit the ground? We are looking for time. And so now we think back through all our kinematics equations and all the stuff we know. In this situation, we've got zero acceleration once it leaves the ground and is traveling along this dotted path. So we need to think back to our section with zero acceleration, our constant velocity objectives. And if we remember that, the only equation that we really had to work with to find values like this was that speed is equal to distance divided by time. We don't have enough information to figure that out. Here we have acceleration, so we have all the constant acceleration equations at our disposal. And given initial velocity, acceleration, and displacement, we can indeed find time if we use the y values. And this is pretty universal, that when you have a projectile motion problem like this, you're going to use the y direction to find time, typically. Not always, but typically. So we list our equation. We know that we're going to use, in this case, the equation that has all of this. It's the initial velocity times time plus 1/2 acceleration times time squared. Our displacement was -16. Initial velocity is 0, so this whole term gets canceled out because 0 times t is 0. And that would be 1/2 times -9.8 times t squared. And solving this for t squared, multiplying these out and dividing and so on and so forth, we get a value of 3.27 for the time squared. Take the square root of this, and we find that the time is 1.81 seconds. And so with that, we found out how long this thing will be airborne. It'll be airborne for almost 2 seconds. Now, for part B, how far from the base of the cliff does the car land? So now we're looking for this distance. And notice that this is in the x direction. And we have an interesting case here. Something kind of fun happens with this problem. And I'm going to list it right over here just so that we can see it with the drawing. If we look at our givens, we don't even have to list the y direction in this, because we know we're looking for something that is exclusively in the x direction. So we really just need our givens in the x direction. That our speed is 20 meters per second. Again, once we leave the ground, we have no force pushing us forward or backwards, so our acceleration is 0 meters per second squared. And we don't know anything else except now our key addition from part A, because this is the same situation, we can use that. We have time, and we want the distance or the displacement. You can think of them either way you'd like in this case. Now, if you think about just these situations of constant velocity, which this is because acceleration is 0, we can just use our equation that speed is distance over time. We know our speed is 20, our time is 1.81, and it's pretty trivial from there to solve for the distance. It's just going to be 20 times 1.81, or 36.2 meters. Here's where it gets interesting though, and this is sort of bonus. We've solved the problem at this point, so you could go on with your life, and that's nice. But what I want you to see is that the situation of constant velocity actually is still using these kinematics equations. It's just that the acceleration is 0. For instance, if I use this equation, that distance is the initial velocity times time plus 1/2 at squared. So again, let me draw a line here to distinguish where we're working this a second way. We'll call this way 1. and this will be way 2. And this is just kind of neat, is that if we plug 0 in for the acceleration, this whole term disappears, and we're just left with d equals the initial velocity times time. Notice that that is no different. That's just a rearranged version of our constant speed equation. So either way you work this is going to work out. In fact, this one is almost easier because now we don't have to deal with the fraction. And I remember being a high school student. Fractions are something you get better at with age, I promise. So if you want to avoid that, this is a nice, easy way, and you end up with exactly the same answer. So all I wanted you to see from that is that these equations are more interrelated than maybe they first appear. But there you go. That's how we solve these projectile motion equations, or projectile motion problems, excuse me, in 2 dimensions. Just remember, you have to work any y-axis problem and x-axis problem separately.